Came up with the ideas about what the planetary motion is based on a model of Copernicus. And he said there were elliptical orbits, and also he said some things about how fast things go around compared to how far they are. But he was able to say that the period of orbits in years squared is equal to the average, I'll just say for now, the average distance A from the sun in astronomical units. That is the Earth distance from the sun, one astronomical unit. And it turns out that ratio is very close to 1 for all the planets. So it's a really remarkable and simple kind of relationship here. The question was, so he understood all the ratios between the planets. So in AU, we know relative to AUs how many years each orbit is of Venus and Mercury and Mars and Jupiter and Saturn at the time. They didn't know about Uranus or Neptune. But they didn't know what an AU was. An AU is the distance from the Earth to the Sun, but was it 1,000 kilometers? Was it 10,000 kilometers? Was it 1,000,000 kilometers? Was it 1,000,000,000 kilometers? They didn't know. So the absolute measure, how big is the solar system? They knew all the relative measures, but didn't know the absolute measure. So a big thing at the time, and it's often talked about when this happens, were transits of planets. Well, I better say, I just say two of them, Mercury or Venus. Now, according to the Keplerian or Galilean, or really ultimately Copernican model, then that's a heliocentric model. Then the sun is at the center, and we have Mercury going around, and Venus going around. The Mercury is about 0.4 AU. Venus is about 0.7 AU. And then Earth is out here at 1 AU. And then the transit of Mercury and Venus basically takes place when Mercury or Venus, respectively, are interpose themselves, or their orbits interpose their disk on top of the disk of the sun. And you can see its position. So, I think we have a picture of that too. Let's see. We have a picture of the second chapter. I think that's that one.
P squared in here is equal to AP, that's roughly,
Oh yeah, that's a square and cube. Let's see, where was it? Oh, here. You know, for example, here's a picture of the sun, and here's that's Mercury. Now, a few years back, we had an annular eclipse, and we also had a transit of Venus. Venus was going by, so I went to one place and another. I think I went to Chabot. It was too crowded. Went over. So okay, there's too many cars. Let's go over to the Lawrence Hall of Science, maybe. But the lines were, there were 500 people online. I was like, forget this. Let's go home. Use a telescope. Okay. So I had this old kind of telescope, and it was kind of broken, but it was perfect for displaying the sun, and you project it out through an eyepiece, say, and then so you get a projection of the sun. You get to see the sunspots and everything, and then you could see Venus. There it was, and it was going across. And so the Venus, say for example, it will go across at a certain, say this is the sun's solar disk, and so you see Venus like there. And then as time goes on, it'll go there, and then there, and go across the sun. At different, as time goes on. Now, if you're at different latitude, then that looks like a different position. So here, if you're on, say, if you're at the Earth, looking at Venus here, and here's the sun. If you're looking from point A, it'll look like it's down there, but from point B, it'll look like it's up there. So this might be the path of A, and this might be the path of someone at B. Now, that basically sets a difference, or we call a baseline, that you can sort of triangulate the distance to Venus, and by using this angle. And so this is called parallax. And so they could figure, knowing the distance between A and B, somebody in Northern Europe and somebody else in Africa, I don't know where it was at the time. Then they got an estimate for what 1 AU was. And so this is based on the idea of parallax. The parallax we use all the time. Parallax, you wouldn't be able to live without parallax. Does anybody know why that is? Everybody uses it every day, all the time, unless you're asleep. Your eyes. You have two eyes, not one. Okay, so we have two eyes, and they're displaced by a certain distance, a baseline. And if you, say, take something and put it in front of your face there, and you put it, say you put one hand over one eye, and then you line that up with something in the background. If you then shift what eye's open, oh, it's a big shift in the background. So you see things that are displaced like two images. If you're focused, you can see one single image, but if you focus at infinity there, then all of a sudden you can see these double images over here. So that parallax gives you depth perception. So your brain has software to, I don't know if it's based on experience, probably, to give you an idea how far something is out from you by the way you see things and focus on it. That's parallax. And so we can do that with planets, we can do it with stars. It's a kind of triangulation. And let's see, maybe I can put up here. Let's see, I don't want to put something up that would be too confusing, but basically the distance, I'll just say parallax. The distance to some distant object is some baseline times or divided by the parallax angle. Now, the parallax angle is in degrees. If it's in degrees, then we have to adjust this thing with a number that has to cancel the degrees somehow. So it turns out that number is 57.3 degrees, roughly speaking. So if you have basically you can look at a star, and then you see the star has a right ascension of such and such. And then you use a baseline, the baseline of just the width of the Earth, the diameter is too small. But if you use the baseline of 1 AU, after half a year, now half a year, say a quarter of a year, say the Earth goes, or let's maybe I better, well, maybe it's best to use this figure. So here, now this says, you can use the Earth at two different places, and you see parallax, but typically what you do is a kind of triangulation, some object in space. But for stars, that's too, that baseline is too small. Maybe you could see that for a satellite or even planets, things like that. Certainly we did here, that was parallax. But if you want to see stars, then let's see if we have a picture of that. No, come on, doesn't have a good picture of that. Okay, I'll have to draw So here's the sun, here's Earth going around, and I'm gonna say, we're gonna have a baseline where Earth is at position A and then position B. Now this is gonna be 6 months later, and the baseline is not gonna be 1 AU, it's gonna be 2 AU. This is 1 AU, 1 astronomical unit, 1 distance from the Earth to the sun. And this is some scale here. Then we might have a distant star out here. But then way, 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 way out is a very distant star. Such that during the year between A and B, these stars don't move at all. So we might have something that looks like this. So at A, this might look curved to you, so I'm going to try to make it straight. Maybe I better get different colors. So say this is A. The line of sight will put it at a certain right ascension. Call it A, right? Or a certain declination. Right ascension and declination. But then 6 months later, it's going to look like this. Right ascension, declination, B. Okay? So it's going to look like it's in a different position. And we said these things don't change, but they really don't change for most of the stars. They don't change hardly at all, because this kind of arc, this angle, we call it the parallax angle. This kind of arc at most is about 1 arc second. Okay. For the nearest stars. The farther the star is away, then that angle gets smaller. The nearer it is, then the angle gets bigger. So here, if you have an object here, you have a big angle. The farther you go out here is a smaller angle. So you use these, say 1 arc second is so small, and it's tough to pick up in even a good telescope. It's very difficult. So you have to have very good astronomical tools to pick this kind of thing up. But they did that for many of the nearest stars. But it probably can only go out to about maybe, I don't know if it's about 1/100th of an arc second, something like that. So then it's even impossible for the tools on Earth to be able to see the difference. But they have a satellite called Hipparchus that is particularly tasked with a mission to find a greater number and farther out stars that we can detect how far they are. So we can see out maybe a few thousand light years, maybe 10,000 light years maybe with Hipparchus, and get star distances. Now you can think of this in 2 ways. You can say, if I have an angle from 2 different points on a baseline, then I can find the distance. The distance is maybe, say the height of that triangle, call it x. So that's the distance, x. And it turns out we can say the distance x in something called parsecs is equal to 1 over the parallax angle theta in arc seconds. And 1 parsec, parsec gets this name from this parallax kind of thing. 1 parsec is 3.26 light years. Light year is, as you might recall, I think we did a computation of that, about 9.46, and that's 10 to the 12th kilometer. So if you have, if something is at, say, it has 1 arc second, of parallax, how far away in light years is it going to be? One arc second gives you how many parsecs? 1/1 is? One. So it's going to be 1 parsec. So how many light years away is it going to be? 3.26. If it has 1/2 an arc second, that means it's farther away. Smaller angle, so it has to get farther away. Then how many parsecs do we have then? Yeah, we have 2 parsecs, which is going to be 6.52 light years. Okay. So the farther, if you double the distance, you halve the angle. Or if you make the angle 1/4, you quadruple the distance for parallax. Now the flip side of parallax is angular diameter. Now, in fact, this is essentially about more about angular diameter. For example, I can look at something out here, like the moon. Say the moon is a certain size, and it has an angular diameter. We call that the parallax angle, but it's basically the diameter. Say the moon at arm's distance is about this size, and that corresponds to an angle of about 1/2 a degree out of the 180 from there to there. So if you know the distance, then you can tell the diameter, the actual diameter. In other words, you can reverse this formula up here. And say, I'm going to be here and look out and see the angular diameter of something. And then I can use this. I'll put it here, angular diameter. We call the flip side parallax. So here, I'll say the angular diameter corresponds to the diameter. The diameter is the baseline. So we can actually compute the diameter by solving for this thing. Instead of calling it parallax, we'll call it angular diameter. And so the diameter here, which is the baseline, is the distance times the angle in degrees, and we just solve for this thing. We just reverse it around. Now, you can, if you know the distance to the moon, 1/2 a degree over 57.3 times the distance to the moon will give you the diameter of the moon, or vice versa. If you know the diameter of the moon, you can get the distance. In fact, the history of discovery of the solar system and various things, the Earth and the moon, and finding out distances, proceeded from Eratosthenes, who found out how big the Earth was. He could do that from a simple geometry based on this idea. Let's see if we have some diagram of that. Oh, here's the angular diameter, just a little bit. So, the same kind of thing. The diameter we called the baseline before. Here's the angular diameter that we called the parallax before. And this is the same kind of thing, the distance. There's a distance on it. So the moon actually looks bigger because it has an elliptical orbit sometimes, and sometimes smaller. That gives rise to the annular eclipse. And if it's bigger, you have a longer solar eclipse, that is, if it's close in. So we don't have such a long solar eclipse in 2017. So it's really farther out. But let's see as we talk about Eratosthenes. No, I think it was just at the end of this. first draft here. I was hoping to see some good picture. No, all right. So basically Eratosthenes was able to find out the diameter of the Earth. He figured, well, if the Earth is a sphere, then let's draw it. And this is the scientific method. So hypothesize the Earth is a sphere, and the sun is way far away. If the sun is way far away, it's sending out rays of light, but it's actually, the rays are diverging. But if it's so far away, almost all the rays are coming in virtually parallel. Whether you're near the equator or not. Maybe here's the equator. So Eratosthenes said, okay, let's find out where a post you put in the ground, vertically into the ground, is vertical with no shadow. Then he sent somebody down here, let's put the post down here. We know how a distance he'd walk because he marked it off in terms of some measure we would call kilometers, but they had another measure called stadia, whatever that means exactly. There is some kind of correspondence there, I just don't know what it is.
That's where our term for stadium comes from. It's about that one.
Yeah, I don't know, that might be half a kilometer or something, I don't know. So you know this distance here, and then they observed this angle, I think was about 7 degrees or something. And so that angle, using geometry, is the same as this angle. Okay? So these two angles are the same. So they knew the angle, and then based on the idea that this is a sphere, then 7 out of 360 degrees is the amount of distance, I'll call it S, over the circumference. So they observed this, hypothesized this relationship because of the sphere, and if we make a guess that there's a sphere, then we arrive at R, given that we measure off S. So just by simple geometry, he found out what the radius was. Then it was Aristotle who observed a lunar eclipse. And he saw that the Earth cast a shadow on the lunar eclipse. How many people have seen the lunar eclipse? I think nobody, right? If you get a chance to see a lunar eclipse, please go see it. But it starts out with basically an arc, and it looks like a big bite is being taken out of the moon. But you can see how big the arc is. And so you might see something like this. The moon. And then you see this arc, that's the shadow, and you know it's coming from the Earth. Aristotle said, oh, look at that curve. That's a curved arc. That arc is curved, but that is an arc, not a line, because the Earth must be round. So he made an inference. Earth is causing the shadow. So the Earth must be round. And this is the size of the shadow. Well, then you know this size relative to the moon, so you can figure out something about the moon relative to the Earth's size. Now the fact is, this isn't really the Earth's size because we know the moon in a full solar eclipse, tapers down to about 0 compared to 1 moon diameter. So he knows that this diameter is actually 1 moon diameter short of the size of the Earth. So then, using the Eratosthenes idea of the Earth, size of the Earth, then he knew the diameter of the moon. Once you know the diameter of the moon, and you know its angular measure, you know the distance to the moon. So that's how you bootstrap your way forward to understand nature. This is the way it sort of happens. Aristotle made many contributions, a lot in the scientific method. Of course, I guess he was a tutor of Alexander the Great. And unfortunately, I have to apologize to Aristotle because I always when I introduce a lot of physics courses or astronomy courses, I go through all the ways he was wrong. And he had a whole bunch of ideas about the universe was wrong. Aristotle, the background of, you know, the ideas of Copernicus and Galileo was that the Catholic Church dominated Europe, and they had backed the ideas of Aristotle. And Aristotle said that Aristotle, Plato, and Ptolemy espoused a geocentric view of the universe. That the natural state of motion always comes to rest. So natural state of motion is at rest. What else? Heavier stuff falls faster. And you can see that, you know, you drop a piece of paper and you drop something that's heavier, gee whiz, you know, that's a no-brainer. Of course it falls faster, look at that. You know, one thing falls faster than the other. But if you get rid of that, some special thing called air resistance, it will fall at the same rate. And Galileo was to be able to see beyond that kind of stuff. And he was able to experimentally show, he believed and showed that heavier things don't fall faster than lighter things, as long as you can adapt the shape to take care of air resistance or drag. Copernicus said it was a heliocentric universe, not a geocentric universe. That agreed with someone called, some by the name of Aristarchus, who was also instrumental in finding out a lot about the distances of the sun and various things about that nature. In fact, I think Aristarchus got to this understanding using Aristotelian kind of base. And there are a couple of other things in here that were disproven by Galileo, Copernicus, and Newton. Of course, this was backed by the Catholic Church, and so the Catholic Church and religion itself, because religion in the Western world was the Catholic Church, began to be seen as suspect. But at the same time, Martin Luther posted his 95 Theses on some major church in Germany, and that was the beginning of the Protestant Reformation, and the base for democracy, free thinking, and the age of reason that was brought about by physics and astronomy. So the age of reason, democracy, all these things, it was a kind of internal reformation of Christianity that freed people's thinking, and so they didn't have to fear the church unless they disagreed with the church. Galileo and Copernicus were afraid to say anything. Galileo Copernicus didn't put his ideas of the heliocentric view of the universe out, publish them until his deathbed. And Galileo was under house arrest because he disagreed with the Catholic Church.
His reputation, his freedom, and eventually his life.
So unfortunately, religion gets a bad name because it backed the wrong course and became too dogmatic. But there's a lot of good in religion, so don't throw the baby out with the bathwater. Otherwise, you lose the baby. It's among the forces.
Did you want us to turn in the packet?
Homework?
Review and discussion, yeah, the homework?
Yeah, sure. Yeah, you can turn in the homework if you want. Yep. I think I said today, so it
Yeah.
should be in today.
And then the exercises?
And the exercises. We can put these up here. Yeah, sure. One for the homework and one for the class.
After this, I try and beat traffic by reading as soon as possible.